Yay!
Yay! Okay, another very typical example of Gauss's law is what we do inside of an insulator, the electric field inside of an insulator, where the charge is uniformly distributed throughout. The usual example that's worked inside the text of textbooks, like inside the chapter as an example, usually they do the sphere, and then they leave this one typically as a homework problem. But it uses the same technique. So this is what happens. What is the electric field inside a cylinder with some total amount of charge uniformly distributed. Okay, so it's not a conducting pipe. It's not a conducting cylinder where all the charge would be on the surface. Right? That would be a lot easier. This is the charge is uniformly distributed throughout the volume of the thing. So it's maybe some sort of an insulator where the charges can't move. And so we want to know at some position here, let's say that it's little r away from the center. What is the electric field at that point inside somewhere? So we use the same technique as you do if it were a sphere, and that is to use Gauss's law. So here's the idea. Gauss's law, again, the integral form says E dot dA, the total amount of flux, right, over the surface is just equal to the charge enclosed, that's going to become important, divided by epsilon naught. All right. Remember, the whole point of doing this is that we don't actually want to do a difficult integral. So since this is true for any surface, for any closed surface at all, we want to choose the one that makes that integral easy. So make the integral easy. How do we make it easy? Well, first of all, we need to get rid of that dot product because E dot dA, you know what that is. That's like E dA cosine theta. And so the last thing I want to do is integrate this thing over a whole bunch of different cosines as I go around the surface, the angle between E and dA. So how do I make that dot product go away? I want to make that into just E dot dA, just E dA, right? Which means I want E to be parallel to dA everywhere. So I want to choose a surface where the surface normals are going in the same direction as the electric field. Okay, so usually all you do is you look at the problem, and based on the symmetry of the problem, then you're going to know what surface to choose. So here in this example, the symmetry is that I know in this surface, because it's got cylindrical symmetry, the electric field is going to be coming off looking like this. Right? And so what surface has surface normals that look like that? Well, a cylinder does. So I'm just going to match the geometry of the problem. And if I choose a cylinder outlined here, I just did the sort of dotted line. If I choose a cylinder to integrate over, and a long cylinder, so I don't have to worry about the end caps, E is everywhere parallel to dA. So I'm going to be fine. That dot product is going to disappear. So this is just going to become EdA is equal to Q enclosed over epsilon naught. All right. Let's see what's next. Next is, to make this easier, I want E, if I've chosen my surface right, the electric field everywhere on the surface of that thing is going to be constant, right? It's going to be uniform, because then I can take E outside of the integral. That'll be very nice. And that's going to happen because, again, just due to symmetry, as I go around this surface, I'm the same distance r away from the center no matter where I am. So the electric field is not going to change, right? So this is just going to be E dA is Q enclosed over epsilon naught. So if my electric field is constant, I can bring that out. And now it's going to be pretty easy. What is dA over a cylinder? That's just the surface area of a cylinder, not counting the end caps. And the surface area of the cylinder, That's just E times, what is it? Well, it's just going to be the circumference of a cylinder times its length. So it's just going to be 2 pi RL is equal to Q enclosed over epsilon naught. Okay, so anyway, the left-hand side, it looks like is pretty much done. I've avoided doing the integral, except to just make it a surface integral, which is easy. Okay, so now on the right-hand side, I got this Q enclosed. How much charge have I enclosed? Now that looks a little tricky. It's not the total Q, right? Because I'm on the inside. So some of that Q is outside of my radius. So I just want to know how much charge have I enclosed with that cylinder. And so here's the trick. It's the same trick you use for computing this for a sphere. And that is, use this. Q enclosed over the total, the amount of charge that I've enclosed over the total amount of charge is equal to the total amount of volume I've enclosed over the total volume. That should be right. If it's distributed uniformly throughout the volume, then that should be true. So the amount of charge I've enclosed compared to the total is just the same. It should be the same ratio as the amount of volume I've enclosed over the total. Okay, well, how much volume have I enclosed? Well, what's the volume of that little cylinder? It's going to be what, the area now of the disk, and then it sweeps out over a length L. So this is going to be pi r squared L. What's the total volume of the cylinder? It's going to be pi big R squared times L. So it's that ratio that matters. So that Q enclosed is just going to be what? Q pi r squared L over pi, epsilon naught pi big R squared times L. Well, nice that the pi and the L's all cancel. So here's what I have at the end. We're basically done. The electric field then, at that point, now I can just get E by itself. And so, geez, what do I have? I got a Q. One of those R's is going to cancel. I'm just going to be left with an R up top. And then the bottom, I have a 2 pi epsilon naught big R squared, I think. Did I get everything? Q, R cancels 2 pi epsilon. I think I got it all. Oh, I did forget my L, right? I should have an L down here. So let's see. If we look at this, I got a Q. Look at this. I got a Q and I got a pi r squared L. That's like a volume. That's like the volume of the thing. So Q divided by volume, that's like a volume charge density, and we called that rho. So another way to write it, I mean, we were already done, that's fine. But another way you might see it written is, that could be the volume charge density over, what do I have left? 2 epsilon naught times R. Just another way to write it. So that's if we're inside. If we're outside, if R is greater, if little r is greater than big R, then what we have is then the amount of charges that we've enclosed, if we're all the way out here, taking a Gaussian cylinder all the way out there, then we really have enclosed all the charge, right? And so this just becomes pretty easy. Then we have E times 2 pi RL equals just plain old Q over epsilon naught. So the electric field is Q over 2 pi epsilon naught RL, like that. But that looks pretty similar to what we had way back when computing the electric field from continuous charge distributions, where 1 over 2 pi epsilon naught, that was 2k, right? And then Q over L, that was our lambda, linear charge density, charge per meter over R, right? So we had something like this. So in other words, if we're outside of the cylinder, it just looks like a line of charge, just like you would sort of expect it to. Okay, so this is how you can get the total electric field inside of a distribution and then outside of a distribution using Gauss's law.